This is bond polarity part 2. We're going to be talking about polar molecules in this. Again, you must have a periodic table out in front of you. And we're going to do slightly more complicated examples. Remember, electronegativity increases as you go up and over. So let's talk about some examples like this with HCN, which you should be able to draw the Lewis dot structure and rapidly come up with this, 3 atoms. And if we look at the periodic table, nitrogen right here is more electronegative than carbon, which is more electronegative than hydrogen. We have dipole vectors in this direction, and from hydrogen to chlorine, so the overall dipole vector is like that, and we would have a partial negative, partial positive up here, and on the nitrogen it's negative, on the hydrogen it's partially positive. This molecule would be polar molecule, and we have a dipole moment. The moment is this vector for this molecule. We have 2 bonds here and here that are polar. So let's try this one. CO3 minus 2. Again, you should be able to do the Lewis dot structure. And before I go out, note oxygen is more electronegative than carbon. We draw the Lewis dot structure and we get something like this. And we rapidly say, okay, that's trigonal planar shape, so we have to draw it differently. And I don't have to put all the electrons on it now. I just need the bonds. And we have 3 polar bonds. We have one like this, one like this, and one like this. This molecule is non-polar. It's non-polar because the 3 dipole vectors here, here, and here exactly cancel. They're pulling in 3 directions. If I thought about these as a rope pulling this way, and this way, a carbon atom would never move, okay? Because we have equal pull in all directions. So it's non-polar, but it does have polar bonds. And we've got to distinguish between talking about bonds and the molecule. The molecule is nonpolar. It has polar bonds. It has a 0 dipole moment. That means the total vector for the polarity is 0. Try SO2. SO2, you should rapidly get the Lewis dot structure. Looks something like this. And that's trigonal planar structure. So we go like this, with the oxygen, and the electron pair. Now remember, all I worry about are the bonds. So I have oxygen is more electronegative than sulfur. They're right here. Oxygen and sulfur's below it. When I look at this, my dipole vector is going to be in this direction and in this direction, and my net dipole moment, which I'll put in green here, is going in that direction. That's the sum of these 2 vectors here and here. It's a polar molecule. It has a dipole moment, and it has polar bonds. Next thing we're going to look at, CCl4. So CCl4, draw the Lewis dot structure, and hopefully you can do this quickly. Here's the Lewis dot structure. These get complicated, and that is a tetrahedral. You really would like to make a model of this. And we have a chlorine out here, chlorine here, chlorine here, chlorine here. I forgot my electrons over here, but I'm not interested in electrons right now, except around the central atom. Okay, so we have 4 dipole vectors. Chlorine is more electronegative than carbon. And so I have one here, here, on this chlorine coming out of the page, and on this chlorine going back in behind the page. And that total dipole vector is equal to 0. Now, if you don't believe it's equal to 0, remember these are all the same. All these chlorines are the same. And so if I rotated this molecule so that this chlorine was down here, I would get the same molecule. If we number this one 1 and this one 2, you know, we would now have 1 up here and 2 maybe over here and 3 up here and 4 up here. Cl1, Cl2, Cl3. So we've rotated all the chlorines, and so if this molecule was polar, then our dipole should be down here, but it is not. Everything cancels in this. They're all pulling equal and opposite directions. It would have polar bonds but it would have 0 net dipole moments. So the molecule would be non-polar. Okay, so the tetrahedral is hard. Another tetrahedral one, NF3. So we take nitrogen, bond to fluorine, 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 and electron pair. That's the Lewis dot structure. Nitrogen, we draw this. I'm going to put my electron pair up here. Fluorine down, and fluorine down and behind. Remember, this triangle's out in front here, and these dashed lines are behind. Okay? And so clearly fluorine is more electronegative than nitrogen. So I have a dipole that way, down, down, and down. And so my net dipole is going to be in this direction, down below the plane of the paper, straight down. The fluorine, if I looked at this from the top view, I would have nitrogen, and I would have a fluorine here, and a fluorine here, and a fluorine here. And so the pole in these directions are going to cancel, but they're all pulling below this plane here, if I put a plane in here. So I have a net dipole down. All right, let's look at water. H2O, oxygen, bond, hydrogen, 2 lone pairs, structures tetrahedral. I'm going to put my hydrogens here, and my lone pairs out here. And so this one's pretty easy. Again, I have polar bonds. The oxygen is more electronegative than the hydrogen, so these are pulling in, and I'm going to have a net dipole in this direction. So another example of a polar molecule with a net dipole moment. But that's about it. You just got to think your way through these. I gave all the types of examples you might have here. One thing to remember, if an atom bonds to itself, for example, C bonds C, that is nonpolar because they share. That's it.